Hello all, welcome back Data Science Brain. This video is part 2 of our machine learning Titanic survival prediction project. In the previous video, we have done exploratory data analysis on the Titanic survival prediction dataset. We have seen how features like age, sex and class decides whether the passenger has survived Titanic or not. In this video, we will be focusing on building multiple models, machine learning models using the dataset, and we will be comparing the models using different hyperparameters, and finally we will select a particular model and we will use it for predicting whether a passenger survived or not in the Titanic. Before we begin, kindly like this video, subscribe to our YouTube channel if you haven't already, and share this video with your friends. Make sure to watch this video right till the end. So now that we are into the model building, we are loading the test dataset into test data variable. We are using the read CSV function from pandas, and we are reading test.csv file into test data variable, and we will be keeping it for later use during the prediction. And after that, one of the important steps before model building is data cleaning. We have done some data cleaning in the previous video during the data analysis, and after that, now we are dropping some of the columns that we don't need for the model building. We know that the name column doesn't really have any impact on whether or not the passenger survived or not. Your name doesn't really matter. Unless of course you are some important person in the country, or maybe a politician or something like that. But the name column generally doesn't really have any big impact on whether or not the passenger survived or not. Also, the passenger ID and the ticket columns doesn't really have any huge impact on the fact that the passenger survived or not. So we are dropping those two columns using the drop function from our trained data. And after that, we are encoding some of the categorical variables. Now we know that we have categorical variables like P class, your class, your economic class, and your sex and embarked. These three columns have categorical variables. So we are encoding that using one-hot encoding technique. We are using the get dummies function from pandas for doing the same. So we are passing in the classes P class, sex and embarked, and we are passing in the training data. And inside the training data, we are telling the function that use the training data, and inside the training data, these are the columns for which we need the one-hot encoding to be done. And this drop first is equal to true means it will drop the first category. So what one-hot encoding does is that it will take, for example, it will take the sex class. Now sex has two categories, right? It's either a male or female. So what it does is that it will turn that one single column into two columns, both having names male and female. So it will turn each categories into a column, and inside that column, if the passenger is male, the cell value will be 1, and if the passenger is female, the cell value for male column will be 0. So similarly for the female column, if the passenger is female, in that column the cell value will be 1, and if the passenger is male, for the female column the value will be 0. So when we are doing drop first equal to true, what it does is that it will drop either one of the columns, because we don't need both the columns to know whether a passenger is female or male, right? Because if we are only having the male column itself, we can see that whether a passenger is a female, because if the value in the male column is 0, it automatically means that the passenger is female. So we don't really need the female column to know whether or not the passenger is male or female. We only need one column after we have done this one-hot encoding. So that's the reason why we are dropping. We are putting this drop first equal to true. It will drop one of the first category that is turned into a column by using one-hot encoding. Similarly, we will be turning the P class categories into columns and also the embarked into columns, and the values will be 0 or 1. So if the passenger is male, in the male column it will be written as 1. If it is a female, it will be written as 0. So like that. Similarly for embarked as well. We'll create what were the classes in embarked. It will be C, Q and S. So in the C column, if the passenger belongs to C, if the passenger embarked from the C port, it will be given the value 1. And if he embarked from the Q port, in the Q column, it will be 1. Otherwise it will be 0. I hope you got the idea. So that's what one-hot encoding does. So the reason why we are dropping the first category is that it is to avoid multicollinearity. So multicollinearity is a statistical phenomenon. So what it means is that it happens when two or more independent variables, two or more features in a data set is highly correlated. So what happens is that the model for the model it becomes really difficult to understand the individual impacts of these correlated independent variables. So to avoid that, we are using this drop first is equal to true. So what does it that it will drop the one of these columns for the sex class. It will drop the female column, so that we know that there are two columns named male and female. Obviously it is highly correlated. We can definitely understand the values of the other column just by looking at the first column. Just by looking at male column, we know what will be the values in the female column. It is highly correlated. Now this will lead to multicollinearity, and it will again in turn lead to unstable model, and the model will find it really difficult to understand the individual impact of these variables, and that is really important, because that's the way in which the model assigns coefficients to the individual variables. Now if the model doesn't understand the individual effects of these variables, it will become really difficult, and it will lead to high variance and model instability as well. So we need to avoid multicollinearity as much as possible, and having two independent variables that are highly correlated will definitely lead to multicollinearity, and to avoid that we are using draw first is equal to true. So to ensure that if there are two categorical variables, only one while we are doing one hot encoding, only one of the columns, only one of the categories, we'll be only keeping one of the categories. The other category that is turned into a column will be dropped. So in this case we will be dropping probably the female column. So the male column will remain, and by looking at the male column we can easily predict what is whether the person is a male or female. So that's about that. And after that we are scaling the numerical columns. So why do we need to do a scaling? So we know that the numerical columns will be having numbers, right? Now the age column will be having numbers ranging from what, maybe 1 to 80. That's the age range, right? We have seen somewhere here. Yeah, it was something around 0 to 80, I believe. And SIBSP will also be having numbers ranging from something like how many siblings. So 0 to maybe 8 or maybe 5 or something like that. Parent and child will also be having values ranging from 0 to 8 or 10 or maybe something like that. The fair column will be having values ranging from 40 to maybe 400 or 500 or maybe 100. So so these numbers in different columns are actually not in the same scale, isn't it? The numbers in the fair column is in a different scale. It will be ranging from, it will be going from like 0, 50, 100, 150, 200, like that, right? If you are drawing a graph by plotting the values in the fair column, we'll be going from we'll be using numbers like 0, 50, 100, 150, 200, etc., right? So it has a different scale. Now the age column has a totally different scale. It is ranging from values ranging from 0 to 100, and SIBSP will be having values ranging from 0 to 10. So the scales are different. So if you do not normalize these scales, what happens is that the model will think that the columns that are having higher values have a high impact on deciding whether the batch survived or not. So it will give more importance to those columns. But that is not the true. That is not true, isn't it? Because we know that the fair doesn't have really high impact. It doesn't really have so much more impact than SIBSP or PARC, like the parent child or siblings spouse column. So that is important. So it is important to scale all the numerical values to an equal scale, so that the model will not give more importance to the numerical columns that have really high numerical values. So we are using min-max scaler for scaling the numerical columns: age, SIBSP, sibling spouse, PARC, parent child, and fair. So we are fitting the numerical columns. So we are fitting these columns from the training data into the scaler. We are defining the min-max scaler here, and we are using the scalar's fit transform function to scale all these columns inside the training data. So this will transform the numerical values inside each numerical columns into a scale that ranges from 0 to 1. So it will keep the range of, the scale of all the numerical columns equal. So that the model won't think that the columns that are having really high numerical values have a really high impact. So this will avoid any kind of bias. And now, after doing all those data cleaning and engineering, future engineering, and all those things, now we are, we haven't done any really big future engineering. Actually, we haven't converted or we haven't created any futures. That's what future engineering is called. But we have some, manipulated our futures and we have done some data cleaning. So now we are splitting our dataset into X and Y. There are categories, features and target variable. So we know that in the survived column is the target that we need to predict. So we are dropping that from the dataset and we are creating the features data, the features variable, and we are using the only the survived column for creating the target variable Y. We are storing that in the small letter y and we are storing the features into capital letter X. Now after that we are dividing it into training and testing datasets. Now you will be confused here a little bit because you have seen me actually loading the test data here from test.csv. Now this test data that we have loaded here will only be used for evaluating, for the final evaluation. After we are selecting, we'll be doing some tests. We'll be seeing some the performance of the model on. We'll be seeing the performance of multiple models. Then we'll be selecting one model based on different hyperparameters which we have tried on. And after that, after we have built the final model only, we'll be using this test data set to test the data, test the model. So for the training purpose, we'll be doing some tests, right? And for that, we are actually splitting this X and Y into X train and Y train, and X test and Y test. So we are using the train test split function from scikit-learn to split the dataset X and Y into X train, X test, Y train, and Y test. So we are passing in X and Y features and target, and the test size is 0.2. That means that 20% of the data will be used for testing, will be stored in the test dataset, and the 80% will be stored into training datasets. And the random state is equal to 42. We are using this. I think I have mentioned this in the previous project. We are using this so that whatever code I am writing here, if you wrote the same code and if you put random state equal to 42, you will be getting the same split for X train, X test, Y train, and Y test. Means this X train, my X train and your X train will be having the same values. Otherwise, it will be random. It will be different. So make sure to put the same random state equal to 42 if you want the same result as I have received. And now we are going to build the model. So we will be, as I have mentioned previously, we will be comparing different models. So here we are importing random forest classifier, gradient boosting classifier, and support vector classifier from scikit-learn library. And we are also importing grid search. So we'll be doing grid search to find the best hyperparameters for all of these machine learning algorithms. So we know that hyperparameters are something that the model doesn't learn itself. We need to set it before we train the model. The model doesn't learn it like parameters. Hyperparameters are something that we need to set it before the training of the model. So grid search, what it does is that it will run. It will input. We need to input a set of hyperparameters. It's like a parameter grid for each of the models that we are going to train. And the grid search algorithm will go through all these hyperparameters values, and it will pick first it will pick one, and then it will train the entire data set on that hyperparameter using that hyperparameters, and it will select the next set of hyperparameters, and it will select the next set of hyperparameters. Like that it will do, and it will do a cross validation or some kind of validation, and it will return us the accuracy or any kind of evaluation metric that we are using, and it will give us the result of the best set of hyperparameters and the accuracy that the particular model received using that particular set of hyperparameters. So this is how we create a grid for random forest algorithm. We'll be putting in hyperparameters like n estimators, maximum depth of the tree. N estimators means how many estimators we need, how many trees we need. So, as you might know that in a decision tree, when it is built, it makes decisions at each node based on features in datasets. Now, the tree will continue to split nodes and increase its depth until a stopping condition is met. Now, in most cases, this stopping condition is a certain depth of the tree. So that's the reason why we have given here different values for the depth of the tree, max depth. So this max depth hyperparameter controls the maximum number of nodes from the root of the tree to the farthest leaf, that is depth of the tree. And it is essential to limit the depth of the tree, preventing it from growing too complex. And a higher max depth value, like a deeper tree, will lead to overfitting, because the model will become too tailored to the training data, the data that we are using for training the model, and performs poorly on new unseen data. So it will become overfit to the training data, and it won't perform well for unseen data. Now we can see that we have given several values here. Now this none value that we have given here, it represents that there is no maximum depth. That means the tree will grow until each leaf node contains a minimum number of samples, which will be controlled by the next hyperparameter. The last hyperparameter, that is min sample leaf, or until all leaves are pure. Now pure means it contains samples of only one class. So, and other values we are given here are 10, 20 and 30. So these sets specific limits for the depth of the tree in random forest. Now appropriate values for max depth will depend on the specific dataset and problem at hand, and that's why we have given here several values. So the grid search algorithm will be able to give us the best set of values. So the next one is min sample split. Now the min sample split is the minimum number of samples required to split an internal node. That means how many samples are required to split the nodes, different nodes in the different leaves in the tree, so that it contains different classes. So now in the process of constructing a decision tree, the algorithm repeatedly splits nodes based on the values of features in the dataset. Now this min sample split determines the minimum number of samples that must be present in the node for it to be considered for a split. If the number of samples at the node is less than the specified value, the node will not be split further, because we cannot actually make a decision based on just single value, right? It'll be too biased. Now a higher value of min sample split leads to a more conservative tree construction. The tree will be less likely to split nodes that have smaller number of samples, resulting in a simpler or less complex tree. It will be risk free, but it will be really low complex. And on the other hand, that will be underfit actually. But on the other hand, a lower value allows the tree to make splits even with fewer samples, potentially capturing more detailed patterns in data. However, this can also, as we have seen, lead to overfitting, as it might capture the noises in the data as well. And it will split the tree using using the insights from the noise data, and this can lead to overfitting. So we have given here several values, and the grid search algorithm will run the model using all these values, and it will give us the best value. So the next one is min sample leaf. Now similar to min sample split, this also decides whether or not have a node. So the min sample split decides whether or not to split this node into two other nodes, based on the number of samples in that node. And min samples leaf will decide whether or not this leaf node represents a final decision. Means the minimum number of samples required to be at a leaf node. Means a leaf node is the final node. Okay, other nodes have different branches, but the leaf node doesn't have any branch. That will be the final node. So this min sample leaves determines the number of samples required for a particular node to become a leaf node. Means the final decision. So in a decision tree, a leaf node represents a final decision or a prediction for a specific subset of input data. The min sample leaf sets the threshold for the minimum number of samples that must be present in a leaf node for making it a leaf node. Now if creating a split if you are splitting a node and that would result in creating leaf nodes with fewer samples than the specified min sample leaf value, then the split will not be carried out. Now, a higher value of min samples leaf will lead to a more conservative tree. Means, it prevents the tree from creating nodes with very few samples, which can help avoiding overfitting, and it will avoid the scenarios where the model will fit to noise data, the training data. Now, in the other hand, a lower value of min sample leaf allows the tree to create leaves with fewer samples, potentially capturing more detailed patterns in the data, but also increasing the risk of overfitting. Similar to the min sample split hyperparameter. Now we have given some values here, and our grid search algorithm will take all these values and put it in the model, and it will train the model, and it will give us the best hyperparameter, which gives the best accuracy. Now moving on, the next algorithm we will be testing is gradient boosting. So gradient boosting is also similar to random forest in a way that it is also an ensemble learning technique. Now the difference between both is that random forest builds multiple decision trees independently, and it will combine the predictions through averaging or voting. But in gradient boosting, the trees are built sequentially. Each new tree will correct the errors made by the previous one. So it focuses on improving the weakness of the model at each stage. Now because of this as well, random forest is easier to, the computationally easier for the for our system, because we can parallelly do calculations for the multiple trees. But in gradient boosting, since it is sequential, each trees are made only after the other one, so it is computationally more costly. And random forest can give us a much more maybe diverse and complex trees in some cases. And also the final prediction is an average of these trees. But in gradient boosting, the errors are corrected at each stage after building each trees. So maybe it can lead to, in some cases it can lead to much better error correction. So the errors are handled by averaging predictions in random forest, and errors made by one tree is corrected soon, in a sequential way in gradient boosting. So let's now look at the hyperparameters for gradient boosting. Now just like random forest, n estimators means decision trees, the number of decision trees. Now gradient boosting also uses a weak learner like a decision tree. Now, so the n estimators means the number of decision trees that will be used for the gradient boosting ensemble learning algorithm. Now learning rate in the context of gradient boosting determines how much each tree contributes to the overall ensemble. Now a lower learning rate requires more trees to achieve the same level of performance as higher learning rate. It's a regularization technique that can prevent overfitting by making the model robust and reducing the impact of each individual tree. Now small learning rate like that we have given here, 0.01, this can lead to gradual learning from each tree. This will require more trees, more boosting stages to reach high performance. Now this will be really slow process, but it will lead to generally more robust, a model that is more robust to overfitting, also a smoother convergence, but in a really slow manner. The next one is a medium learning rate like 0.1. Now this is a balanced trade-off between speed and model performance. Now depending on your system and your your system's ability to computational ability, you can choose a medium learning rate. Now this is a commonly used practice. Higher learning rate will be useful when you need a rapid learning from each tree. So this can lead to faster convergence but may risk overfitting. This requires fewer trees but may be more prone to capturing noise and becoming overfit. So we have given here some of the values that can be used for the grid search algorithm to test our model and give us back a good accuracy with a perfect hyperparameter. Now the next one is a max depth. Now just like in the random forest algorithm, the max depth defines the maximum depth of the individual trees. Now it controls the maximum depth the height of the tree from root node to the leaf node. Now a larger value, as we have seen in random forest algorithm, allows for more complex models but obviously increase the risk of overfitting. In sample split again is the same like in random forest, it defines the minimum number of samples needed to make a node split. Now mean sample leaf, just like in random forest, it is the same thing. Since we are using decision tree in gradient boosting as well, it defines the minimum samples required for a node to become a leaf node. Now the sample is too less than, the number of samples are less than the number we have mentioned in the min sample leaf, the split won't happen and the leaf node won't be made. So those are the hyperparameters for gradient boosting algorithm. Next algorithm is SVM, support vector machine support vector classification algorithm. And hyperparameters are C, gamma, and the kernel will be using for the support vector classifier. So I hope you know that what a support vector machine is. It's a supervised learning algorithm used for classification and regression. And in this particular case, we'll be using the support vector classifier for classification. Now what it does is that it finds a hyperplane that separates data points belonging to different classes. Now a hyperplane is a binary, in a binary classification problem, a hyperplane is the decision boundary that maximally separates the data points of one class from the other. And support vectors, as the name suggests, are the data points that supports the hyperplane, that are closest to the hyperplane, and it plays a really crucial role in determining the position of the hyperplane. Now let's see the hyperparameters. Now hyperparameter C is the regularization parameter. Now C controls the trade-off between achieving a low training error and a low testing error. A smaller C will encourage a larger margin separating the hyperplane even if it misclassifies more training points. And a larger C penalizes training errors more heavily, potentially leading to a smaller margin hyperplane. Now the gamma hyperparameter defines the coefficient for RBF, radial basis function, and the polynomial kernels. Now we'll be seeing the kernels as the next hyperparameter here. So the gamma defines how far the influence of a single training example reaches. So a low value means a large influence and a high value means a smaller influence for a single training example. Now how it affects the shape of a decision boundary. So a small gamma will result in a more generalized decision boundary, and a large gamma will make the decision boundary more dependent on single training example. So it will become more dependent on the training data, and it will become overfit. So next one is kernel. So the kernel specifies the type of the kernel hyperparameter specifies the type of kernel used in the algorithm. So the kernel function transforms. It is what is transforming the input data into a higher dimensional space, making it easier to find a hyperplane. Now common choices include linear kernel, RBF, radial basis function kernel, which is suitable for non-linear data, and polynomial kernel. So these are some of the most popular kernels that we can use for the support vector classifier. So these are the values that we are given here. We have chosen linear and RBF. RBF for non-linear data and linear kernel for if there is any linear data. So these are the three algorithms that we'll be using for the grid search algorithm to find the best model and the best hyperparameters for that particular model. Now here I have written the same thing that I have explained here about all the hyperparameters. This for you to have a quick look when I be sharing this IPYNB file in the description. And the next step is to define the classifiers. So we have defined random forest classifier, gradient boosting classifier, and support vector classifier using these variables RF, GB, and SVM. And after that, we will be passing in these classifiers into the grid search algorithm, the grid search function. We will be passing in the classifier here, first RF classifier, random forest classifier, then the parameters for that particular classifier, the parameter grid for that particular classifier, and CV. CV means, so we need to evaluate the model, right? We need to validate the model, and here we are using cross validation. We are using cross validation with 5 folds. So this is a k-fold cross validation and with 5 folds. So CV equal to 5 means it is a 5-fold cross validation we are using for validating the models. So it is taking the random forest classifier model, I mean the algorithm, and with this hyperparameter grid, and will be doing a cross validation with 5 folds for giving us the accuracy and the best fit parameters. And we'll be fitting this grid search algorithm with the training data. And similarly, we'll do the same for gradient boosting and SVM as well. And we'll uh, fit the grid search with the training data. And after that, we'll be after training this, we'll be printing the best parameters. We'll be using best params from the grid search algorithm, and we'll be printing the best parameters and the best score, the best accuracy score that we have received for those parameters for each models for random forest, gradient boosting, and SVM. So we can see that random forest has achieved an accuracy of around 83%, and gradient boosting has achieved the accuracy of around 82%, and SVM has received an accuracy of around 81%. And we can see that the best parameters for random forest are maxed up this none. So it has gone till the last node. It has taken the maxed up as none. So it has gone near the maximum fit of the model, the maximum fit the model can give. And also min sample leaf, it has taken us 2, min sample split as 5, and n estimators as, so it has only taken 50 trees. So only with 50 trees and with a max depth of none, it has given us an accuracy of 83%. So this random forest algorithm has the best accuracy out of all the 3 algorithms. So we'll be choosing this for making our final model. So we will make the final model using these hyperparameters. N estimators as 50 trees, and depth of none. Depth of none means it will go as deep as possible until the max sample leaf limit reaches. And min sample split as 5, so it means that it needs at least 5 samples to split a node. And min sample leaf 2 means that the leaf node needs at least 2 samples for being a leaf node. And random state is equal to 42 means exact same thing. So what this is that it will make both of our, I mean the whoever is coding alongside with me will see the same output as I am seeing. So it's a seed that is used for reproducibility. And after that, we will be fitting our model using the training data, X train and Y train, and we'll be training the model. And after that, we will create we will predict this test data. We will pass in the test data and we will get the predictions. And then we will use the accuracy score from a scikit-learn metrics for getting the accuracy of our model. We'll be comparing the Y test with the Y prediction, with the prediction that we have made here by passing in the X test data. And we already have the Y test data with us. So we'll be comparing the Y test, the original actual outcome with the predicted outcome. And the accuracy score will be printed as 84%. So we can see that our model was able to predict predict the data with make the predictions with an accuracy of around 84%. That's a fine accuracy. As I have already mentioned in the data cleaning part that we haven't done any feature engineering or anything. We have just cleaned the data and selected the features that we thought might be helpful, and we have made a model, and it has performed 84%. It has performance of 84% accuracy, and that is fine. Okay, with more feature engineering and all those things, you can actually improve this to more than 95%. Okay, this is not the best, but it is something good. So we have received an accuracy, and now we can move on to predicting the data for using the model on datasets that it hasn't seen before for a new dataset. So as we have seen before, we have already loaded the test data here from the test.csv file. We have already loaded the data and kept here in the test data variable. So we have to do all the data cleaning that we have done on the training data on this test data as well. So we will remove all the all the null values by using median or any other techniques, median mode or common value techniques. And we will be dropping all the features that we have, all the columns that we are not using in the training data. And also we will one hot and got the categorical values, and also we will scale the numerical values. So this all this data cleaning and data transformation will be done on test data as well. And after that, we will be passing into the predict function of our model that we have created using the training data, and we will get the new prediction. Now to compare, to see if our predictions are true, we don't actually have the actual prediction values. We only have the test. We only have the features data. Don't have the class data with us. So one thing we can do is that we can actually add another column to the test data called survived prediction, having the that column will have the values of our from our new prediction variable. So this will be the predicted values. We will add that column to the test data, so we can actually compare, because we have done the data analysis, right? We have done exploratory data analysis, so we know that which features will, which values of particular feature will actually lead to the survival of the passenger. So we can actually kind of guess from this data whether or not our prediction is correct. So I have actually printed only the survivors, printed the column, printed the rows with value 1 in the survived prediction column. So that means that all these rows represents survivors, represents passengers that are survived. So we can say that as in our, yes, we have seen in our data analysis, we know that people who embarked from port C had a higher chance of survival. So port C is in given here, but from this, if these two are false, it means that the passenger onboarded the ship from port C, and we can see that he has survived. So we can see that most of these values are false. At least more of these values are false. That means that more people who embarked from port C survived, and that and we know that that is true from our exploratory data analysis that we have done in the previous video. We know that people who embarked from port C had a higher chance of survival. So our model has correctly predicted this. And also we can see that if the P class was 1, if your class was 1, if you belong to a class 1 passenger, then you had a higher chance of survival. So we can see that also again more of these values are false. So it means that the passenger belong to class 1. Also one of the biggest impact was for the column named sex. We know that females had a really high chance of survival. So we can see that if your sex was male, you can see that if your sex is in male, if the column sex has false, it means that you are a female, you definitely had a higher chance of survival. So all the people here who survived, actually most of them who survived belong to the female sex. So from this, and comparing this with our data analysis that we have done in the previous video, we know that our model has actually done a really good job in predicting whether or not the passenger survived. Just by looking at this sex column, we know that all of these are false. That means that all of these passengers who survived are females, and we know that it's a fact from the data analysis that we have done in the previous video. So our model has done pretty well. So that's all about this project. I hope you have liked this, and it's not a really extensive project. It's a simple project that anyone can follow. I wanted to make it like that, so that everyone who is starting out in machine learning can also follow this. This is really simple. All the data analysis and everything is clearly explained, and it is really simple. And I'll be sharing this code in the IPynb file in the description below. If you like this video, kindly support us by sharing this video with your friends, and subscribe to our YouTube channel if you haven't already. And I'll see you in the next video. Till then, happy coding. Thank you.